What's up, young mathematicians? Today we're going to talk about arithmetic sequences. And yes, that is how you say the word when you are talking about sequences, not arithmetic, arithmetic. First, let's talk about what a sequence is. A sequence is a function whose domain is a set of consecutive integers. If a domain is not given, we know that the domain starts with 1. The values in the range are the terms in the sequence. A finite sequence has an end, an infinite sequence goes on forever. A sequence can be specified by what we call a formula, an equation, or a rule, and we'll see that below. So here's two examples of sequences, 19, 26, 34, 41, just some pattern of numbers here. It looks like in this case, these numbers are increasing. Now this one goes up by 7, this one goes up by 8, so there's really not a pattern, but this is some sequence of numbers. Now, what's important here is what we said about if a domain is not specified, it's a set of consecutive integers. So this is the sequence, 19, 26, 34, 41. We could kind of think of it as a table. This is the first term in the sequence. This is the second term. This is the third term. This is the fourth term, and that would continue. So the values of the domain are 1, 2, 3, 4. The values of the range are 19, 26, 34, 41. Same thing here. Here's another type of sequence that we'll study in a future unit. No domain is given, so we assume that the first term we see is the first term in the sequence, and the next one is the second term, and so on. So domain values 1, 2, 3, 4, range values are the actual terms of the sequence. All right, in this section, we're really concerned with arithmetic sequences. And what is it that makes a sequence arithmetic? It is the fact that there is a common difference between consecutive terms. This difference could be a positive number. This difference could be a negative number. So if we look at this sequence, what do we do to go from 5 to 9? We add 4. From 9 to 13, we add 4. From 13 to 17, we add 4. So since there's a common difference between all of our terms, this is what we call an arithmetic sequence. Same thing here. Well, let's take a look. Actually, what's going on from negative 26 to negative 32? We're going down 6. And then from negative 32 to negative 38, we're going down 6. But from negative 38 to negative 45, we're going down 7. So this is actually not an arithmetic sequence because the difference isn't the same all along. All right, so one of the main things we've got to be able to do with these sequences is to find what we call an explicit formula or an explicit rule for the sequence. And what this does for us is it will allow us to find any term number in the sequence once we have this explicit formula. So here's the formula. A sub n equals a sub 1 plus n minus 1 times the common difference. On your formula sheet, this is the way the formula is written. I often will write it with the common difference on this side of the parentheses, since I like to distribute from the left, but it's all the same. A sub n is referring to the nth term. Like if we had a sub 41, that would be referring to the 41st term. A sub 1 here in the formula is the first term. N is a particular term number in the sequence, and D is the common difference between terms in the sequence. All right, and we could also write a recursive formula or recursive rule. That means the same thing. And here it is. A sub n equals a sub n minus 1 plus D, where a sub 1 equals blank. Whatever the sequence you're dealing with, you will specify the first term. This a sub n minus 1 just means the previous term. So the recursive formula gives you a certain term number based off the previous term plus the common difference. How is the recursive formula useful? If we're given a recursive formula for a sequence, we can then use the information in it to write the sequence. Then from there, we can figure out other information. And you'll see that applied later on. So example 1, determine if each sequence is arithmetic. If it is arithmetic, state the common difference. Now, you can often fairly easily just figure out, okay, what am I doing to go from negative 43 to negative 32? Well, we're going up 11. What are we doing to go from negative 32 to negative 21? We're increasing by 11. Negative 21 to negative 10, same thing. So this sequence is arithmetic, and the common difference is 11. For B, let's see, from 14 to 18, add 4. From 18 to 22, add 4. From 22 to 27, we add 5. So this one is not arithmetic. All right. So this one's not really that difficult to see what the difference is, but let's just suppose we couldn't tell. The way you figure out what you're doing from one term to the next is to take a term and just subtract from it the previous term. So we could say 12.3 minus 14.6, and that would give us a negative 2.3. And we could do that for each difference, and you would see that we get the same thing. So this sequence is arithmetic, and the common difference is negative 2.3. Now, on example D, I can really tell if I'm flipping back between positive and negative, negative and positive, positive and negative, that this sequence is not going to be arithmetic. We could find these differences and would see that they are clearly different. Okay, so that's how you determine if a sequence is arithmetic or not. Look for that common difference. So here's this explicit and recursive rule or formula we were talking about above. So here's a sequence. Find the explicit formula and the recursive formula. Well, to write these formulas, you need two things. You need the first term and you need the common difference. All right, do we have a sub 1? We sure do. That's negative 10. Can we fairly easily figure out the common difference? Yes. That's easiest to find out up here where the numbers are positive. What's 14 minus 6? That's 8. So we can just take that information and plug it into the formula. A sub n equals a sub 1. Now, like I mentioned above, I'll write the difference on this side. Okay, so let's plug that information in. A sub n equals, what is a sub 1? That's negative 10. Our difference is 8 times n minus 1. Now, we're not going to leave it like this. We need to simplify it. So a sub n equals negative 10 plus 8n when we distribute minus 8. Then we just need to combine the negative 10 and the negative 18. So that would give us a sub n equals 8n minus 18. Now, hopefully you're recognizing that this is basically just a linear function. We have our slope and we have our y-intercept, which leads me to how I would normally figure out this sequence kind of a quick way or a shortcut way, or this formula rather. We can see that the difference is 8, so we know right away that's our slope. So I would write a sub n equals 8n. Here's my slope. And now we know all we're looking for here is a y-intercept. Well, we know from previous study that the y-intercept occurs where the x value is 0. So let's think what we said earlier about this sequence and our a sequence and how the first term is term 1 and then we have the second term and so on. So what we need is term 0, and the output at term 0 would be our y-intercept. So instead of adding 8 to go forward in the sequence, we would just subtract 8 to go backwards one spot in the sequence, and negative 10 subtract 8 would give us that negative 18. So I usually find my explicit rule, the shortcut method, but I wanted you to see the formula, how it's plugged in, and how it's simplified, and what it should look like. All right, now we also need to give the recursive rule here. So the recursive formula was a sub n equals a sub n minus 1 plus the common difference, and we have to state the first term. All right, so for this sequence, it's going to be a sub n equals a sub n minus 1. It starts out this way every single time, even when we get to geometric sequences in a future unit. The recursive rule will be a sub n equals a sub n minus 1. Okay, and here we just put in the difference. In this case, it is a positive 8, so we have plus 8. And then we say, well, the first term is negative 10. So there is the recursive formula. So here was our explicit rule. I'll write it by this one, explicit, and this was the recursive formula. All right, let's find both of those for this next sequence. And I'm going to use the shortcut method here. Arithmetic sequences are linear because they have a common difference. So I'm also going to use a different variable. It doesn't always have to be a sub n. You'll see that in a couple problems below. I use t. You'll see that in other texts. Doesn't really matter. It's referring to the same thing. So pretty easy to tell here our slope. What's happening? We're going down 6. So there's our slope. Well, I need the 0th term, so all I have to do is go back 1 term. So instead of subtracting 6, I'm going to add 6. So what would 117 plus 6 be? That would be 123. So plus 123. There's our explicit rule. Explicit. All right, and recursive, a sub n equals a sub n minus 1 starts out that way every time. Next, we put in our difference, which in this case is negative 6. And we must also specify our first term, which is 117. So you can see, you can figure out these two formulas without having to do a whole lot of work. All right, examples 3. Find the indicated term of each sequence. So this is really what the explicit form of a sequence is used for, finding particular term number. So we want to know the 50th term. Well, we've got the first 4, so we could continue this pattern 46 more times. But there's a quicker way for us to get that, to just come up with that explicit formula and then plug 50 into it. So I'm going to go the shortcut method, a sub n equals, well, what's my common difference in this sequence? It is 7. So that would be 7n. That's basically our slope. Now I need the y-intercept, so all I would have to do is to go back 7 instead of up 7. So what would that be? 43 minus 7 is 36. So there is the explicit formula for this sequence. So if I want a sub 50, I'll just plug 50 in. All right, so what's 7 times 50? That's 350 plus 36. That gives us 386. So a sub 50 is 386. So again, once we find that explicit formula, we can figure out any term number in the sequence. All right, let's do the same for this sequence. Notice we did use a t here. I'm going to find the sequence the shortcut way. T sub n equals, what are we doing here? Looks like we are going down 15. So there's our slope. How do we find our y-intercept? We just add 15. So if I go 60 plus 15, that would give us 75. So there is our explicit formula for this sequence. And if I want term 19, I'm just going to plug 19 in. So t sub 19 equals negative 15 times 19 plus 75. T sub 19 equals, let's plug that in our calculator, negative 15 times 19. All right, negative 15 times 19 and plus 75. So what does that give us? That gives us negative 210. So t sub 19 is negative 210. All right. Next type of problem is finding an explicit rule given the recursive rule. So the recursive formula tells us where to start our sequence. So that would be negative 40. And it tells us that there's a difference of 8 between terms. So we would go up to negative 32. And then we would go up to negative 24. And then we would go up to negative 16. So there is the sequence defined by this recursive rule. And if we want to find the explicit rule, yes, we could go back to the formula, but again, I like the shortcut method. So a sub n equals, well, that's given to us, the difference, 8. All we need to do is go back to the 0th term, which would be negative 48. So there's the explicit formula given this recursive formula. All right, E for explicit. All right, now we've got our recursive rule defined here. T sub n equals T sub n minus 1 minus 4.5, where T sub 1 is 14. So our first term is going to be 14, and from that we'll just subtract 4.5. So that would take us down to 9.5, and then 9.5 minus 4.5 would be 5, and 5 minus 4.5 would be 0.5. So that's what this sequence would look like. Let's find the explicit formula. So T sub n equals, I know this is my slope term, negative 4.5 n. And then all I need to do is add 4.5 the other direction to get my 0th term right here, which would be 18.5. So there is the explicit formula for this sequence given that recursive formula. Notice I use the words rule here. I want to see how you can use those. I want you to see how you can use those interchangeably. All right, let's write an explicit formula from some different information here. We've got a little bit more work to do on these problems. So we have a sub 13 equals negative 31 and a common difference of negative 75. So what we need to write an explicit formula is either to know the formula, or I'm sorry, to have the sequence so we can find the difference and then go back to the 0th term. Or if we know the common difference and a sub 1, we can plug it into the formula. Well, we don't have enough information to get the sequence right now. So what we're going to have to do is use the formula and work backwards this time. That's why I wanted you to see the formula at least once in a previous problem. So a sub n equals a sub 1 plus the common difference times n minus 1. Yes, remember the d could be over on this side of the parentheses. I prefer to have it over here. So let's plug in what we know. We know that the 13th term of this sequence, which 13 would go in for n, is negative 31. So we'll put negative 31 in here. A sub 1 is what we don't know yet. The difference is negative this time, so it's negative or minus 7.5. Now, this negative 31 was term number 13, so 13 goes in for n, and minus 1 is just in the formula. So here we have negative 31 equals a sub 1, and when you multiply negative 7.5 times 12, we get negative 90. All right, we will add 90 to both sides, and when we do that, we get that a sub 1 equals 59. All right. So we now have a sub 1. We know the common difference given to us in the problem. Now, you could write out a formula and then do the shortcut method, but I am going to go back to the actual formula here. I just said you could write out a formula. It should have been you could write out a sequence. But yeah, I'm going to go back to the formula. So the formula is a sub n equals a sub 1 plus common difference times n minus 1. All right, so a sub n equals, what is a sub 1? It is 59, and our common difference here is negative 7.5 times n minus 1. All right, so we have a sub n equals 59 minus 7.5n, and then plus 7.5 when we distribute. So final answer for our explicit formula, our slope term will go first, negative 7.5n, and 59 plus 7.5 would be 66.5. So here's the explicit rule for a sequence from this given information. All right, so part B, or example B, what do we have there? We have the fact that the 10th term is 35 and the 17th term is 56. All right, so what we're going to do is treat these like two ordered pairs, and we're going to find the slope, which is just the common difference in the sequence. So what we have here is an input of 10 with an output of 35, or the 17th term, that's an x value, being 56, that's a y value. So we can find the slope of these two, between these 2 points. So we would have y sub 2 minus y sub 1 over 17 minus 10. Well, what does that give us? That gives us 21 over 7, or 3. So we now know that our common difference between terms here is 3. All right. So we're going to use the formula and work backwards again. Now, would it be that difficult to write out the 10th term and then just go back 9 spots to find the first term? That wouldn't really be that awful, but I do want to use the formula again. So using the formula, a sub n, well, I'm going to go with this first point. So the 35 is equal to a sub 1 plus our common difference, which we just found to be 3, times n minus 1. Well, n is 10 this time. All right, so we have 35 being equal to a sub 1 plus, let's go ahead and do two things at once here. 10 minus 1 is 9. 9 times 3 is 27. Subtract 27 from both sides. Subtract 27. What's 35 minus 27? That is 8. So 8 is our first term. All right, so I'm going to write out the sequence this time instead of using the formula to find the explicit rule. So the first term of the sequence is 8. Common difference is 3, so next we would have 11, next 14, next 17, and so on. So finding the explicit rule from the shortcut method, a sub n equals our common difference, which is our slope. Go back one step to the 0th term. So 8 minus 3 would be positive 5. So there is our explicit formula for this sequence from that given information. All right, we've got two word problems, and that will be it. So if there are 20 rows of seats in a concert hall, 16 seats in the first row, 18 seats on the second row, and 20 seats on the third row, and so on, how many seats are on the second to last row? So what I like to do on these is write out a sequence if I can. First row, 16 seats. Next row, 18. Next row, 20. And that pattern continues. So can we come up with an explicit formula for this? Yes, pretty easily. With a shortcut, a sub n equals difference of 2. So there's our slope. Go back to the 0th term. That will be 14. So the formula a sub n equals 2n plus 14 is a rule that describes the number of seats on any given row in this concert hall. We want to know the second to last row. Well, if there's 20 rows in this concert hall. That will be row 19. So we're looking for a sub 19. So that equals 2 times 19 plus 14. So that will be 38 plus 14. Or on the 19th row, there are 52 seats. Okay, one more. You have decided to start collecting coins. After 1 week of collecting coins, you have 12 coins. After 2 weeks, you have 24. After 3 weeks, you have 36. So we could write a sequence for this situation: 12, 24, 36, and so on. Let's make up a sequence, and let's call it C sub n for coins. What is our slope term, or our difference is 12. Now, if we went back 12 to the 0th term, it would actually be 0. So our y-intercept is 0 here. So here's the explicit rule. C sub n equals 12n, where n is the number of weeks. Well, let's see. How many coins would you have in your collection after 1 year? 52 weeks in a year. So C sub 52 would equal 12 times 52, which would give you, see, 52 equals 624. And we could write out the units here, coins. All right, so there are arithmetic sequences.